Hello, my name is Muhammad Osama and I am going to present my paper Adversarial Attacks on Cognitive Self-Organizing Networks, the Challenge and the Way Forward. My co-authors on this paper are Dr. Junaid Qadir and Dr. Ala Al-Fuqaha. During the course of this presentation, I'll follow the following outline where I'll discuss the problem and motivation, then I'll talk about the methodology, and finally we'll talk about the results. So first I'll discuss the problem. Cognitive self-organizing networks are expected to address the challenges of network operation that arises due to complexity, heterogeneity, and diversity, and they are expected to use AI to develop optimization, healing, and protection algorithms to maximize the network coverage and capacity and to reduce the operational expenses of the networks and other related benefits. So AI and especially machine learning will play a critical role in developing CSON systems. Adversarial, so since machine learning is playing the critical role, a very big limitation to machine learning is adversarial examples. Adversarial examples are worst case domain shifts of data set examples which mislead ML based classification or prediction techniques to malfunction with very high probability. For example, this is a machine learning system which is performing classification between three classes. So for the case of lion, it is giving us 0.99, then for the car it is giving a certain probability, with the traffic light it is classifying with a certain probability. So when I introduced a noise in these pictures or introduce a domain shift or adversarial perturbation in these images, they'll start classifying these images into another class with very high probability. Like for the case of lion, we can see that this is a line at the input side, that this is a line at the input side, but it is classified as a pelican with probability of 0.97, or this is a racing car, but it is classified as a speedboat with probability of 0.97. So adversarial attacks on machine learning is a very big threat, and we intend to highlight this threat via this paper. So machine learning, so given a DNN, a function f, where we have an input feature vector x and a y is an output probability vector, adversarial perturbation is created using input feature vector and a perturbation in that vector. So that perturbation, this delta is added to the input example, and a new input is created, and this is called the perturbed input, and this perturbed input is optimized by using a certain optimization function, where the objective is that we need to create a certain input example with minimum amount of perturbation, that when added to the actual input and subjected to the deep neural network, classifies that input into another class. So motivation behind this paper is that we want to highlight the effect of adversarial attacks on cognitive self-organizing networks, and we are the first one to actually do that. And then we want to highlight the level of threat that is hanging upon ML based CSON algorithm. So throughout this paper we intend to answer following questions. Number one, do machine learning techniques used in CSON provide necessary robustness required to deal with adversarial perturbations? Number two, how to build deterrence against adversarial attacks in CSONs? And finally, do the deterrence techniques against adversarial examples creates an arms race between adversaries? So through this paper we want to make the following contribution. To the best of our knowledge, we have made the first attempt to show that CSON utilizing ML techniques are very vulnerable to adversarial attacks. Number two, we also want to highlight that the existing defense against adversarial perturbations are not appropriate for CSON. And finally, we also want to highlight that these perturbation will also and these perturbation and defense schemes will also create an arms race in the CSON. So now we'll talk about the methodology. So first we'll talk about the threat model. So we have selected white box adversarial attacks. So assumption in white box adversarial attack is that adversary knows about the model architecture and the hyperparameter and the input data, and adversary can only perform attack during testing phase. Poisoning attacks are not within the scope of this paper, so we'll only talk about the attacks on the testing time, or otherwise known as evasion attacks. And the goal of these attacks are to compromise the integrity of the deployed machine learning based networking technique. So here by integrity I mean reduction in the accuracy or targeted misclassification. So we have considered security as a case study, and in security we have chosen malware classification as a case to highlight the level of threat. Since there does not exist any standardized malware classification model based on machine learning, so we took the liberty of coming up with our own model. So we have used convolutional neural network based malware classification model, and we have used a malware image data set, a very highly cited data set, and then we have achieved like 98.39% of the classification accuracy on 25 classes, and which is actually the state of the art accuracy on the used data set. And this is the model that we have used. We have used 3 two-dimensional convolutional layers and then a final dense layer with softmax activation function to actually collect the classification probabilities. So so now we talk about the adversarial attacks that we have performed on the particular classifier. So first we have performed fast gradient sign method, and then we have performed basic iterative method, and finally we have performed Jacobian based saliency map attack method. So fast gradient sign method is one-step gradient update along the sign of the gradient to solve the adversarial attack optimization problems shown earlier. So formally the perturbation is calculated as a gradient, as a sign of the gradient of the loss function multiplied with a smaller quantity. This perturbation is then added to the actual input example, which creates an adversarial example, and then this adversarial image will fool the classifier. Similarly, BIM is a method of improving the success of FGSM by iteratively applying it with smaller step size for generating adversarial examples for physical word applications. So here x subscript n plus 1 is an adversarial example, and it is FGSM attacks applied iteratively to create different adversarial examples for physical word applications like malware classification. Jacobian based saliency map method. This attack is an iterative method for generating a saliency map to find out the most discriminant features. So finding most discriminant features in the data is very important. So once you find the most discriminative feature in the data, then you start perturbing them to change the classification output. So this attack is based on calculating the Jacobian of the forward propagating example with respect to the input sample. Once you have made the Jacobian based saliency map, so then you start perturbing the most salient features heuristically, and finally you get to an example which fools the classifier. We've also tested the available defenses against these attacks. So first defense was adversarial training. So we train, so once we have generated the adversarial examples, so we include these example in the training set. So once it is trained on, once the model is trained on the adversarial example, the purpose of this training is to regularize the ML technique. So once it is regularized against the adversarial example, ML technique will become robust against the adversarial example that it is trained on. Then another defense, a network distillation. It is a training process to increase the difficulty in the adversarial example generation. It is based on hiding the gradients between pre-softmax layer and the softmax output. And these and there are also other types of defenses, but we have chosen the two most commonly used defenses against adversarial attacks. Since we are considering only white box model, so we have only tested adversarial training, but a network distillation will also be helpful in this scenario. Now we'll talk about the results. First, we have applied FGSM attack on malware classifier. And this table is highlighting the test accuracies before and after adversarial training. So the test accuracy of legitimate sample in percentage is nearly 99%. Nearly 99%. So when you start throwing adversarial example on that classifier, so the accuracy falls from 98.39 to 1.87, which is actually a loss of like 97%. And when you retrain your model with adversarial examples, or which is also called adversarial training, so after that the recovery of the model increases as you start increasing the epoch. So at the end we have like 97.43% accurate classifier, which is also robust against FGSM based adversarial attacks. So take home message from this slide is to, as shown by the results, FGSM is very basic but lethal adversarial attacks. Adversarial training, as I've shown you earlier, adversarial training improves the ML classifier robustness but takes more training epochs to produce results. Like if you want results equivalent to like 98.3%, you need to retrain your classifier with adversarial example for around like 100 epochs, which is actually which gets more complex and more expensive as your data grows and as you train more. BIM attack on malware classification. So now we've performed another attack called BIM. So BIM is since we know that it's a iterative attack, so test accuracy on legitimate sample is like 97 or 98%. Once we have performed BIM attacks, so this accuracy falls to less than 1%, which is like loss of 96%. And then after adversarial training, the accuracy improves, but that is not acceptable for any CSON application, because still the loss in the accuracy from before and after the adversarial training is like 20 to 30%, as described in column 3 and column 5. So difference between each column is like 25%, which is not acceptable. So take home message from this slide is that BIM is an extension of FGSM attack. Iterative nature of these attacks make it more damaging to ML based CSON applications. And as shown in results, the adversarial training is not able to improve the robustness of this classifier. Then we have performed a different kind of adversarial attack called Jacobian saliency map attack. So in this attack, the accuracy of the classifier on the legitimate sample was around 97%, and when adversarial attack was performed, so the accuracy has fallen from 95.93% to 9.13%, which is like 85% loss in accuracy, but to achieve this accuracy we have to perturb like 90% of the features, which is actually changing the whole data. So this is a very surprising result actually, because GSMA produces state-of-the-art adversarial examples for computer vision and language processing, but in case of malware dataset, this attack produces actually the worst results, and because actually we are changing the whole data to achieve adversarial examples. So for dataset in consideration, GSMA required on average 90% feature alteration for producing adversarial examples. So the take-home message is from this slide is that performing gradient-based forward propagation based attack on especially malware image data set needs more needs very high amount of feature perturbation to achieve adversarial examples. So this is the take-home message from this slide. So we set out to answer the following questions at the beginning of this presentation. First question was the robustness of ML or DL for CSON. So our results have highlighted that ML schemes in their current form are not useful for CSONs, and we need to come up with some sort of design or mechanism to actually make these ML and DL schemes more robust against adversarial attacks if we want to use it for CSON systems. And then we have the second question was the deterrence. So our results also highlight that although existing defense such as adversarial training, it does not improve actually, because in case of BIM adversarial training was not improving any results. And at the end, if you closely look at the results, you will find that the attacker and the defender, they both are using machine learning techniques. So if so that will create an arms race between them, and we need to come up with we need to take care of these arms races before we start utilizing ML or ML algorithms for CSONs. Finally, we have also faced few issues during this experimentation. The first issue was the standardized data set. We don't have standardized data set in networking, so we need to come up with those data sets so that networking community can experiment with them to improve the robustness of machine learning and deep learning for networking examples. And we have also seen that a lot of data get wasted. We only learn from metadata or headers. So we have a lot of other type of network telemetry data, and so we need to also include that data in terms if we want to make ML more robust against these adversarial attacks. And we also need to come up with different ML and DL mechanisms to improve. We need to come up with new models specified for these network data. So this is also a very important research area. Finally, the concluding remarks. So we have demonstrated that network data is highly susceptible to adversarial attacks, and we have also highlighted that without taking into account the adversarial threat, the use of MLDL will also cause a significant security risk, and this is the major hindrance in the deployment of these networks. During this presentation, I have used the following references, and thank you very much for listening patiently. And I've also given my email address at the beginning, so feel free to send me a question. I'll be happy to answer that. Thank you very much.